Hello, everyone. Great. So, hi, everyone. Good evening. My name is Gabriela, and I'm here to talk to you about trustworthy platforms in practice, or as I like to call it, I have a TPM, now what? So, a little bit about me first, the traditional who am I? I'm a security researcher at Nokia Bell Labs during my day job. During the evenings, I'm a compulsive knitter, as this scarf can clearly show. I've been doing research for the past 2 years in trusted computing and root cause analysis. And lately, I've been taking a look into firmware security. So that's a bit what I'm going to discuss today. So a simple question. What happens when you boot your machine? Usually, you power it on. Then after some time, you see the bootloader. And then you go to your favorite Linux distribution, or Windows, or whatever floats your boat. But I actually started wondering, what happens in this little bit between the power on and the actual bootloader? There's quite an important thing, and quite a lot of things happening during this time. So this is when firmware runs. And firmware sits, like if you think of your computer as a stack, you can think of it as there's a layer of hardware, then there's a layer of firmware that abstracts this hardware onto the operating system. And then on top of the operating system, you have the hypervisor or your bare metal applications, and then further up you can have your cloud applications. So firmware has quite an important role. It provides abstractions and hardware initialization. It provides the interface to actually start your operating system, and it restricts access to privileged resources, like the SPI flash, so you can't just write into firmware. Another thing about firmware is that firmware is everywhere. It's in every device you connect into your computer, it's in your computers, it's in your phones. It's in so many places that there's actually this nice talk called battery firmware hacking, where this guy called Charlie Miller talks about how he reverse engineered and hacked the firmware of some Apple batteries, because batteries have firmware to allow the OS to measure the temperature, how much battery you have left, and so on. And this research had actually made it so that you could make this battery catch on fire or something by modifying the firmware. So, hey, it's everywhere, it's quite privileged code, maybe we should be taking a look at it. And the main motivation for firmware research, or this research I do, I always talk about the Snowden leaks. So back in 2013-14, when Snowden was revealing all his secret documents from the NSA, one of these revelations was the fact that the NSA was spying on Cisco and other big companies. They were inserting backdoors in their firmware. And the way they did it is that, well, Cisco would create their products and send it over to the customers. And then the NSA would actually intercept these deliveries, move them to a secret little room, modify the firmware, reflash it with a firmware version that had a backdoor, and then send them over on their way. And that way they had a backdoor into these products. And, well, the customers had no way of knowing if their firmware was OK or not. Cisco didn't know about this. And not only Cisco, they did this to many other companies. It's actually funny. If you go to this A&T product data database, they have this web page that collects all these documents of the Snowden revelations. And it's like browsing a catalog for your favorite exploits, depending on whether you want to exploit a server, a firewall, a phone, you name it. And I find it funny also that it's quite old technology. This exploit is from 2008, for example. Makes you wonder, what are they coming up with now? And, well, firmware is quite important. Nowadays, a couple of years ago, they discovered the first UEFI bootkit in the wild. This was quite an interesting attack because, I don't know if you're familiar with a module called CompuTrace. A lot of laptops, especially corporate laptops, have this module in their firmware. So the way this module behaves is that on boot, the CompuTrace firmware code gets executed, and it basically implants a backdoor into the OS so that you can always have access or a backdoor into that computer in case it gets stolen or lost or something, so that you can recover files or wipe the machine or something. So it's just like a bootkit, except it's good. So what these attackers did is that they actually took this firmware module and they modified it so that the backdoor that they implanted was malicious, and they get a remote code execution vulnerability. And well, the nice thing about this bootkit is that it can actually survive across reboots and across hard drive changes. So since the code is in the firmware itself, even if you change the hard drive or you have your OS and you plug in a new hard drive, you're still going to get that backdoor. So hey, firmware is quite powerful, and maybe we should be looking at it. And a lot of researchers are looking at it, which is quite cool. So this is how I decided to get started in this research. And let's get a bit of context. Let's take a look at how does UEFI boot work, because up until a few months ago, I didn't know either myself. And I just want to have a little disclaimer. Today I'm just going to be talking about x86 boot for UEFI machines. Any other architectures and platforms are out of the scope of this talk, just so you know. So the boot process. It usually starts out with you power on your machine, and then the first stage of the UEFI boot process is the secure boot up stage. So this is code that is run from a little piece of the SPI flash that is read-only memory. It's called the initial boot block. So you run the first code that gets everything initialized in your platform so that the next stage, called the pre-EFI init code, can run. This component has an easy responsibility. It's supposed to enumerate all the devices that it finds attached to the motherboard. It doesn't initialize them, but it does like a recon phase of knowing, OK, so I have this network device, this hard drive, this and this and that. And it prepares the environment so that the driver execution engine can run. In this stage, the driver execution engine is a sort of orchestrator. So its responsibility is to take this table of devices that the pre-EFI component found and tell them, hey, I see you, you're a network interface card. Go initialize yourself and then tell me if it worked or not. So all of these devices that are attached to your computer get to execute their own firmware to initialize themselves. So this is a place where a lot of code gets executed. And then it moves into boot device selection. This is the part of the boot where you look at the drives where you can boot from, and according to the boot order defined in your firmware, then you decide, OK, I'm booting from my hard drive or my USB stick. And then you move, all of this up until now had been executed code from the SPI flash. And now when you move to the transient system load and final bootloader stage, this is the stage where grub will run. So UEFI has this, what they call a transient bootloader, which is just a piece of code that will find where your grub bootloader or your Windows EFI bootloader is, and it'll let this run. And finally, when UEFI stops executing, it still keeps some code, some functions that it exports as runtime services for the OS to use. So all these privileged, so doing firmware updates, for example, are still managed by the UEFI code, and they provide this code as some sort of interrupts or calls in a runtime services table. So we're talking about this because we want to know, well, where can UEFI be attacked? And well, the first obvious candidate is the SPI flash. So a part of the SPI flash is read-only memory, the initial boot block. But the rest of the SPI flash, where most of the firmware code lives, is modifiable. So if an attacker manages to rewrite some of the modules in UEFI so that they execute malicious code, bam, they get a well, they get code that gets executed right before your OS or any of your main protections get in place. And then x86 machines have this interesting mode, this SMM, which is the system management mode, which is the most privileged level at which code can run. This is the kind of code that will take care of things like upgrading firmware. One attack vector is to actually modify SMM code, so do some privilege escalation. The SMM code is actually located in a different part of physical memory. It's protected. When SMM code runs, all the CPU stops any other thing that's being executed. It suspends everything and only lets that code run. So it's the most privileged mode that the CPU can run in. So it is a target for attackers. So UEFI actually has some write protections to the SPI flash, because it would be kind of dumb to let anyone modify the SPI flash. So the first protection control that the BIOS offers is called the BIOS control bit protection. It's just a bit that's turned on or off, and it tells you if you can write to the SPI flash or not. And this is not very useful, because if an attacker actually manages to get SMM privileges, they can just rewrite that bit to be whatever they want. Then there's a second kind of protection for the SPI flash, which is called a protected range. So this is a bit more advanced. With this kind of protection, you can divide the SPI flash into different regions, and you can define policies for each of these regions that say whether you can write or not to them. And the interesting thing is that the SMM code doesn't have the privileges to change these policies. So this would be quite a good protection, except for the fact that many vendors don't implement this. And the reason I find a bit stupid. So when these protected ranges are in place, if you want to update the firmware, which is something that the OS will want to do, if you want to update the firmware from the OS, you have to write the new firmware you download into memory and trigger a reboot automatically, so that upon reboot, that code gets copied to the SPI flash and you boot from it. But many vendors actually want to write directly to the SPI flash so that they can delay the reboot, because the user doesn't want to reboot every time. Like, if you download an update, the user will probably try to say, later, you know, and then user satisfaction is the most important thing, which means these protections often go unimplemented just to make the user's life easier. Then another target of attacks are the option ROMs that get executed during the driver execution engine stage. So during this stage, this component tells, let's say I have a network interface card, and the UEFI BIOS knows about it, and it says, hey, initialize yourself. If this device has compromised firmware itself, this optional code that is being loaded, then it gets executed, and it can potentially put in a backdoor into our system. There's actually a nice example of this kind of attack called Thunderstrike 2 by Trammell Hudson. They actually modified the firmware of a Thunderbolt cable, so that when you connected the Thunderbolt cable, it executed malicious code that would put a backdoor in your system, and if you plugged a new cable that was clean, it would infect the new cable. So it was this kind of malware in option ROMs. So it is a valid attack vector. Then, if you go higher up in the layers, you can modify the bootloader. For example, if you take grub, you can modify what grub is loading, what commands it's executing. That is one thing to do. Or you can add a new bootloader or a new boot option altogether. Stick your evil USB stick, let some code run. So UEFI, to protect itself from this, they implemented something called UEFI Secure Boot. And this works as follows. So your computer turns on, and then the firmware will take the code from that initial boot block. It would check that it's signed by the key from the manufacturer. It'll check that it is correctly signed, and if it is, it'll let this code run. Then the firmware code will do this same verification for the bootloader before it lets the bootloader execute, so that if it's correctly signed, then the bootloader can run. And then the bootloader will check the kernel signature and then let the kernel run if it's OK signed. And the kernel will check the kernel modules so that only signed kernel modules get loaded. And if any of these signatures are not valid, then we get this nice secure boot violation screen. And it halts boot, and your machine doesn't boot until you fix it, until you load actually signed components. So secure boot relies on 4 different databases. The first one is the platform key. This is a key from your firmware manufacturer. It tells you who's allowed to sign the firmware or the firmware modules that go into your system. So for example, from my machine, my platform key, this is a Lenovo laptop, so I have a Lenovo key in my platform key. That makes sense. Then the next database we have is the key exchange key database. So this database contains all the keys or certificates that are allowed to sign UEFI code and kernel modules. So here I have Lenovo keys and Microsoft keys because, well, this machine comes with Windows usually, and Microsoft has their own signing keys. Then we have the DB database, very creative naming. This is a whitelist database. So this contains hashes of good components. So when you are checking a component, you take a hash of it, you check the signature. If it's in this database, it's good to go. And well, here I have I have 2 Microsoft keys that will be able to sign my UEFI components. And then finally, there's the DBX database, which is just like a revocation list. So if you have any known bad modules, you would add their signature to this database. And my database is quite big. I don't really know what's in there, but it's a revocation list. So if any signature is in here, that is a bad component. But usually when I talk about secure boot, even though it's like quite nice technology and it will prevent these unauthorized code modules from running on your machine, I argue that verifying signatures is not enough. It's good, but it's not the whole picture. So one example why I say verifying signatures is not enough is the shadow hammer attack against ASUS. So I think this attack has been discussed in this community quite a lot, but just to make the story short, the ASUS Live Update tool got compromised so that it would actually do a firmware upgrade on the system, and it was a malicious downgrade, so to speak, and they introduced a backdoor into the firmware. And this all went unnoticed for quite a long time because all the binaries were signed with ASUS keys. They were old keys, but they were still ASUS keys. So signing is not always the answer. So, okay, if verifying is not enough, what else can we do? And let me introduce you to the TPM. The TPM is this little chip that's available in many server class hardware laptops. I think both of these laptops have one. And it has nice little features. So the first of them is the notion of a permanent identity. So this little chip comes with a seed that's burned into the chip at manufacture time. And this is unique per each chip that gets manufactured. And from this seed, you can generate 2 key pairs, an endorsement key and an attestation key. And these are keys that are, the endorsement key is a key that's limited to doing encryption and decryption in the chip itself. And the attestation key is a key that's restricted to doing signing inside the chip itself. And these 2 keys give the chip a sense of identity, because no other chip, so you can't read the private part of these key pairs. The TPM can use them, but you can never retrieve them. So if you get something that's signed with one of these keys, it means that it was signed inside this TPM chip. And this permanent identity idea is quite nice. Then it can do some crypto operations, so encryption, decryption, key generation, and so on. It's quite slow, but it has those capabilities. It has a random number generator. It has several counters, like a clock counter, number of times that the chip is power cycled, number of times it goes into hibernation mode, and these kind of things. And then perhaps the most important or the most relevant feature for my talk today is the secure storage. The TPM provides secure storage in the form of non-volatile RAM and platform configuration registers. So here we're going to be focusing on these platform configuration registers. These are 24 registers that can store hashes, either a SHA-1 hash, SHA-256 hash. And you can store into these registers hashes that represent what state your computer is in. So we'll take a look at how that's done a bit later. But I just want to make clear that when I talk about TPM, I talk about the standard, or TPM is a standard made by the Trusted Computing Group. And many different companies have their own version of TPM. Google has OpenTitan, which is a TPM with a little bit of extra functionality on top. Same as Microsoft has Project Cerberus, which is a TPM for their cloud platforms. Amazon has the Nitro security chip, and Apple has their T2 chip. So it's technology that's been widely used, or many companies are actually using this technology. And one nice thing you can do with TPMs on top of secure boot is something called measured boot. So the idea in measured boot is we don't want to stop any components from running. We want to let anything run, but we want to measure each component that runs so we know what was run in our computer. So here we start from the initial boot block. The initial part of the firmware is the core root of trust measurement. That's why the CRTM name. It'll verify itself in the form of it'll take a hash of that code, and it'll store it in the TPM. It doesn't do the signature verification. It just stores a hash into one of the PCRs, one of the registers in the TPM. Then, before it lets the rest of the firmware execute, it'll take a measurement of that firmware, store it in the TPM, and then let the firmware execute. Firmware, in turn, will measure the bootloader, store the measurement in the TPM, let it run, and the bootloader does the same for the kernel. Take measurements, store them, and let it run. And nice thing about these registers that the TPM has is that you don't just write to them. In order to write a value into one of these registers in the TPM, you have to extend it. So when you take a hash of some code, you tell the TPM, OK, store this hash. And what the TPM will do is it'll take the value that's already in the register, it'll concatenate the new value that you're telling it to write, hash this together, and this is what actually gets stored in the TPM, which means that effectively, by the time we're done booting, we have a chain of trust established by all the components that were extended into each of these registers, which is a nice feature because it enables us to do this thing called remote attestation. So remote attestation is the process by which we can retrieve these measurements from the platform and then make a judgment whether this platform is in a good state or in a bad state. So notice that there's a shift here in thinking. So in secure boot, you just prevent any unauthorized code from running, whereas here we let it run, but then we check later if it's what we expect or not. Remote attestation is the process by which a challenger will usually contact some sort of attestation server and ask about some platform, let's say platform A, with a TPM. So the challenger asks, is A trusted? Then the attestation server has the responsibility to actually ask this server, computer, IoT device, whatever it is, hey, can I get your measurements? The device will return these measurements, which are signed with one of the keys I talked about earlier that are unique to that TPM. Then the attestation server will check if this measurement is what I expect it to be. So usually according to some sort of reference machine with a good software and firmware stack built. And then it'll make a judgment and say, hey, yes, A is trusted, or A is not trusted. And one thing you might be wondering is, well, what do these measurements look like? They sound interesting. And they're not really that interesting. There are a bunch of hashes. So these are the platform configuration registers. And you store hashes in them. And these represent the state of one of my machines. And the thing is that you might be wondering, well, what does that mean? That's just a bunch of hex numbers. What do I do with this? And the thing is that each one of these registers has a meaning. And whenever you boot, the firmware has the responsibility to create a boot log. Every time you measure anything from firmware or your bootloader or your kernel, a boot log event gets generated and gets stored somewhere in your machine. So the Trusted Computing Group also defines a standard for what kind of logs do we get, what kind of things can we measure in firmware, according to this TCG PC Client Platform Firmware Profile Specification. Oh, that's a mouthful. So yeah, they define an event log that is generated during boot time. And in the event log, you're going to store the hash that you're telling the TPM to extend into the registers. So effectively, if you get the event log, you're able to rebuild the PCR measurements and know, well, what things generated this end hash. And that's going to become useful later on. So these event logs are exposed through a runtime service from UEFI to the OS. And the OS can choose to store it somewhere, move it from boot time to runtime. So usually they can store it in SecurityFS or something similar. And yeah, as I said before, the log will allow the challenger to verify how were the registers actually constructed, because it has all the values that you tell the TPM to extend into the registers. So the event log, an event log entry can be in one of two formats. The first one is a SHA-1 format, which is a legacy format for TPM version 1.2. So there's this old 1.2 TPM version, which is now obsolete, and now there's TPM 2.0 version. So this legacy mode event log format has every entry has the PCR you're writing to, what kind of event this is, some identifier, the hash that you're extending to the PCR, the size of the event data, and then some sort of event data that describes what you measured. Then in TPM2, we have the crypto-agile log format, which is kind of similar to the previous log format, except that it supports more hashing algorithms. So the first format only supports SHA-1 hashes, and then the second format can have up to as many hashes as your TPM supports. So as I said before, every PCR has a meaning. So PCR 0 is usually this initial boot block, the core root of trust for measurements. And then PCR 1 is usually your BIOS configuration, so everything you change in the BIOS, if you turn on secure boot, turn off secure boot, I don't know, change the boot order, these kind of things. PCR 2 and 3 store measurements for the UEFI code and the configuration for this UEFI code. PCR 4 stores boot manager code, so usually your bootloader, and how many boot attempts it can store event logs for every time you try to boot into some boot option. And yeah, PCR 6 is manufacturer specific, so usually there's not much there unless your manufacturer tells you what they're loading. PCR 7 is used for secure boot policy. 8 to 15 are reserved for the OS. 16 is debug, and 23 is application support. And this sounds great. Every PCR has a meaning, so it must be super easy to figure out what it means, what's happening with my platform. But then I started wondering, well, what happens when things go wrong? What happens when your measurements are not what you expect them to be? How do you deal with this situation? So there's two ways of thinking about it. The secure boot way means, well, you're verifying signatures, so you don't let that code execute. In measure boot, since we're storing hashes of every component, you let any code run, and then you verify later, like what were the measurements of these components that you run. And here I try to go for the measured boot option, because if a platform fails, like if it's a consumer laptop, it's okay to use secure boot. You probably don't want your machine to boot any unauthorized code. But if you think of like large data centers, maybe some more critical platforms, you might actually want to investigate what is happening. So my machine is not in the state I expect it to be, but I want to know why. I don't want to just stop it from executing the code. I want to know what happens and do some forensics and some investigation. So my goal was to use logs to actually investigate these trust failures, building some sort of framework so that I can pinpoint what part of my system I should be checking in detail, because it's not realistic to all the time check all the parts of my machine, especially if I have many, many machines. So I started wondering, OK, can I use the event logs for this? And then I started working with the logs in practice. According to the standard, it should be fairly easy. Everything's defined. Standards are always great, right? Well, not necessarily. The Linux kernel actually added support for moving the event log from the UEFI boot time to the runtime into the OS ever since kernel 4.11. But I found that these logs are actually hard to find. So far, the only Linux distro I can find the logs during the runtime is Fedora. So here I have examples from some machines I have. Fedora has my boot log in SecurityFS, but then I think this is CentOS and Ubuntu. They're not moving the log, even though the code is in the kernel and these things are running same kernel version. Some distros actually provide you with these logs. Some other distros, well, you don't need them. It's probably that no one is asking for it. So that was one struggle I found when working with these logs. I actually had to use some specific OS. Then there's a problem that in the standards, there's a lot of these manufacturer-specific log entries. So parsing these logs is quite tedious. You have to figure out each event has a different kind of data in it, and you have to parse them. And some of them you don't know how to parse because the manufacturer decides what they put in there, and the manufacturer usually doesn't document what they're putting in there. Then I had the problem of different event log formats. So in some machines, the firmware actually lets you pick what kind of log format do you want to use, whether you want to use the legacy mode with only the SHA-1 hashes, or if you want to use the new 2.0 mode. And I found some platforms where the logs, even though there was a TPM 2.0, the logs were stored in legacy mode. And there was no way of changing this. So it changes the whole way. Then you have to write 2 different parsers for the logs. And it just piles up. I just wanted to do something. And oh, wait, there's a lot of rocks, little rocks in the way. And then the final problem I had dealing with these logs were missing events. So when I would see something like this, I would say, hey, cool, I'm getting 11 different registers with measurements. I must be measuring a lot of things. Like I'm verifying everything in my firmware. But if you actually notice, these events, these hashes are all the same, which was, wait a minute, that's not very realistic. What's happening here? And once I actually got to parse the logs and check what was happening, I found out that, well, only one event is being stored in these PCRs, which is a separator event that tells you that the firmware has moved execution from boot time to runtime. So it's not really measuring much, which, OK, it can be a bit misleading. So it takes me to my main problem with firmware, which is the fact that you have the open source implementation for UEFI firmware. It's called Tiano Core. So the UEFI standard defines what UEFI should be like, and there's a reference implementation that's open source. That's cool. Then manufacturers and original equipment manufacturers, so OEMs, they take this open source reference implementation and they modify it for their specific platforms. They add magic. And then what you end up is with absolutely proprietary software or firmware. And you don't really know what it's doing, because a lot of the features just don't get documented. And you're there stuck like, OK, well, what do I do now? How can I still use these logs? But I was determined to use these logs somehow. And I started wondering, well, how far will this open source UEFI implementation take us? What can we actually measure and guarantee if we're going to call our platforms trusted? So I set up a small demo. I decided to go the virtualized way. So I set up a QEMU virtual machine that was running with a TPM 2.0 emulator, and the open source implementation for UEFI that's called OVMF, the Open Virtual Machine Firmware. And I used Fedora Server 31 to be able to get boot logs. And I decided, well, let's build a visualizer for logs so that I can investigate trust failures from the TPM. And well, now I have a small demo of what I actually built, so I can show you what we can change. And I think the screen should change now into my other laptop. Went to sleep. Just a second. Demo effect. OK, there we go. OK, so first of all, I start my TPM 2.0 emulator. And then I start my virtual machine, which is running the OVMF open source implementation of the UEFI firmware that I compiled. So I start running that. If I can enter my password. Yeah. So we can see that things are getting written into the TPM. It's doing something. Well, it's booting my open source UEFI firmware. So OK, let's load Fedora 5.4. And it starts initializing all the modules. So you can see, where's my cursor? Here, some things get written into the TPM while it's booting. Takes a while. It's doing all the measurement, initialization, and so on. So we can wait for it to boot. Right. OK, it's doing stuff. And there we go. I have my Fedora machine, so I can log into it. And the first thing I'm going to show you is what remote attestation looks like. So I have my attestation server, which is this entity I can ask, hey, tell me if a machine is trusted or not. So I have my Fedora virtual machine being monitored by this server. And, well, I have some details about my virtual machine. I have the IP, which is conveniently localhost, because I didn't want to connect to the network here. Then I have these keys that identify the TPM, the public key, the private key. The two public keys, the attestation and the endorsement key. I have information about what kernel is running, what OS. And then I have a policy for my machine, a firmware policy. This policy is simply a mapping between what kind of measurement I can take and what's the value I expect it to have. And then based on this, I do some very simple rules to evaluate if my machine is trusted or not. So I check, can you actually see? I check that the machine has the correct system measurements, that the measurements are signed in a valid manner, and then that it has some valid fields in the structure. So I can actually go and check that my virtual machine is in a good state. I can reattest my virtual machine, and you can see, well, it went by too fast, but when I do the attestation, it's doing stuff on my TPM. So it's getting the measurements, and then, well, I get the results. The machine is good. So what I'm going to do now is we're going to tamper with this machine. So for this demo, I actually prepared a different version of the OVMF firmware, where I've modified with one of the components that gets run during boot time. So I Just a second. Right, so here I'm running my virtual machine, but now the firmware that's being running is OVMF Disobey. So once I actually run this virtual machine, I've tampered with it, and we can soon see that I've changed the boot image. So it's a simple change. I'm not really injecting malicious code, but I am changing something in the firmware. This would be the equivalent of rewriting the SPI flash. And now, just to show another kind of tampering that can be done, I'm actually going to boot from a different kernel, previous version of the Fedora kernel, so 5.3, which is different from what we booted in before. And yeah, well, it's going to take a little while to boot again, and we can see that measurements are happening in our TPM. So just wait a second. Yeah. Yeah, it's doing things. It's measuring the components again. It takes a while, and I should get my logging prompt soon. Yes. Yes. And now we can actually go and reattest the machine. So this would be done automatically in a normal setting. Demo effects make it so that I have to press buttons. But we take our Fedora virtual machine and we reattest it. And when I refresh the page, you can actually see that it's not trusted anymore. So something turned red. OK. Then I can actually go into the details of the machine, and it's going to tell me, hey, your measurements are all wrong. And OK, that is something. Now I know my Fedora virtual machine is not trusted. But I want to do more than that. I want to know, well, what part of it is it not trusted? Is it the whole thing bad? Like, what should I focus on? So I have this little script that will take the logs from the virtual machine. And then now I can show you my visualizer. So the latest two, just a second. Right, so I start my visualizer with the two latest logs. So I have a boot log from the previous time I booted, and I have a boot log from this time I booted my machine. And it should be available here. And you can see, well, I have a list of my PCRs, and there's quite some changes. So I can see PCR 0 changed, PCR 4 changed, PCR 8 and 9 changed. So OK, this gives me more of an indication. So if we go by the standards, we remember these all have different meanings, depending, like they all represent roughly one component or the other in the BIOS. And then I created this kind of like visualization that lets me know how many events are there for each PCR. So the inner ring, each number represents a PCR. And then the bigger the slice, the more events or the more things that were measured into each PCR. So in PCR 0, I can actually see there was a change. Something was different before. And I can see if I'm going to move really quickly into, like, between these two events. And you should see that these hashes change. So some part of the firmware, something that starts in this address, has changed its contents. And this would be the Disobey logo showing when I boot my machine. So then this would give me the indicator. So according to this is a platform firmware event. So since PCR 0 changed, and I can see from the log that this specific hash changed, I know, OK, maybe I should go into the firmware image and check what has changed in this address. So I get some extra information for doing my forensics. Then we can do the same for each PCR that changed, basically. So right now it's very rough and manual, but ideally, this could be automated because all the information is there. So for, So for BCR4, I can see that, let's go to BCR9, having a bit of demo effect. BCR9 contains the measurements of the kernel that's being loaded, which is the other thing I tampered with. So you can see here that the measurements of the kernel and the init RD have actually changed because I booted from a different kernel. So the idea of this demo is to kind of guide my forensics analysis. So if I have many machines, and one of them has a trust failure, one of them gets compromised, changed, attacked, whatever you name it, then I can detect it using remote attestation, and I can use the logs to actually do a deeper analysis on what has changed in that machine. So then you can use tools like, there's this thing called UEFI tool, and I don't know how visible it is there, but you can dump the firmware image, and then you can actually go do detailed analysis and see what address, what offsets things are, and you can see differences between previous states and current states. So that is the end of my demo, and I guess we should change screens back. Yes. So as I was saying a little while ago, well, why are we doing this at all? And the main motivation is this. If you think in a larger scale, we're not going to really have UEFI tools for each one of our machines in the data center to check that the firmware hasn't changed. That's not really realistic. So I think that remote attestation can be used as the first detection protection, so to speak. And then when something changes, we can go and do a deep analysis, and we can use these logs to guide where we go and do this analysis. Well, this is incomplete, yes, event logs are not perfect, but I don't think it's a waste of time, because there's a lot of things we can measure with the logs that UEFI measures. So we can detect things like changes in the BIOS, changes in firmware, changes in the secure boot keys and databases, changes in the boot order, and changes in the kernel. So, okay, there's some things defined by the standards, which would be really cool to detect that I haven't been able to detect yet, like measuring the BMC code, if you think of like data center servers, measuring non-host platforms, and measuring the table of devices that are actually attached to your motherboard. These are things that should be possible to measure, but then it's up to the firmware manufacturer, or the person who actually writes the firmware, to decide what they think is important to measure or not. So does it mean we should stop caring about this because it's not perfect yet? I don't think so. So I liked what Benjamin was saying this morning, that we shouldn't complain that things were much harder back in the days, and that we should be looking forward to how we can improve things. So to end this talk, I just want to raise a bit of awareness. I'm actually quite happy that lately there seemed to be a shift towards open source firmware. So a lot of security researchers are taking a look into firmware, and there's a lot of initiatives to actually build firmware open source. So, well, we already have open source OSs, and if you see the attackers, how they have been moving, it's been like a race down to the bottom of the machine, so to speak. So I think with the more firmware attacks, we can benefit from actually having these kind of open source platforms and transparency and, well, knowing what's happening, because we can only defend against the things we can measure or guarantee. So security by obscurity is not really going to cut it. So on that happy note, I'll finish my talk, and thank you for your attention. I'll be happy to take any questions now.